Hi, welcome to Dr. Raz the Baking Chemist on this foggy, cold, freezing -1 degree afternoon. Right, today's question is all about period 3 oxides, periodicity. It's a year 2 question where only 23.6% of the students got full marks. Really? Let's see where they went wrong. Okay, so it's a multi-part question. We'll see how far we get to. Okay, the elements sodium to sulfur in period 3 all react with oxygen to form oxides. Oxides. So this is all about oxides, and that's it. That's another issue. Yeah, students need to read the question. Okay, according to the examiners, students kept talking about throughout this question. They kept talking about elements rather than their oxides. Okay, the question isn't about elements, the question is about oxides. Okay, period 3 oxides. Give an equation and 2 observations, so 1 equation and 2 observations made for the reaction that occurs when sodium is heated in oxygen. Okay, now there's no denying this. This topic, period 3, is a small topic in year 2, period 3 oxides. However, you've got to sit down and you've got to revise it. Yeah, there's a bit of understanding involved, which I'll highlight in a second, but most of it is revision, memorizing. Yeah, you literally sit down and memorize the equations, okay? As I say, you do need to understand some of the equations, but most of this topic is just memorizing, okay? And there's no two ways about it. Use, revision cards, okay? All right, anyway, so sodium is heated in oxygen. Now, sodium is heated in oxygen, guys. If you do not know this equation, right, and that could only be for one reason, and that's because you don't know the formula of sodium oxide. All right, and if you don't know how to make formulae of ionic compounds, you need to go back to your GCSE principles. Okay, so sodium and plus oxygen. So most people will get that. Okay, but they'll struggle with the formula, and some people did not write down the correct formula. Okay, right. Obviously, we need to balance it. It's an equation. So 2 sodiums there. So if I just put 2 sodiums there. Oh no, hold on a second. 2 oxygens there. I still need 2 oxygens, so I'm going to have to put 2 oxygens here, and that'll give me 4 sodium. So therefore, I'll need 4 sodiums there. Okay, so 4 sodium plus oxygen gives you 2 sodium oxides. All right. And does it mention state symbols? Nope. So I can leave it like that. Okay, but it does ask you for 2 observations. All right, so observation and observation 2. Now you should know, again from GCSE, and even if not from GCSE, then flame colors, yeah, from A levels, year 1s, that when you burn anything that contains sodium, you get a yellow flame. So first observation could be yellow flame. In fact, let's just do this. Put it in here. Okay, so this could be, so just writing the equation down. Observation, well, as I said earlier, yellow flame, right? So, anything that contains sodium, it's yellow flame. Shows the color of the flame is yellow, right? So this should be yellow flame. That's your first observation. Oh, flame, not observation. Right. The second observation is when that sodium has burned and you get sodium oxide, you actually get white solids. Yeah, most of the period 3 oxides are all white solids with the exception of one. And that is sulfur, yeah, sulfur dioxide, which is a gas, yeah. So you'll see, possibly, when this is formed, a white solid. Right, next move on to the next question. Give an equation and 1 observation made for the reaction that occurs when phosphorus is heated in oxygen. So, okay, so give an equation and 1 observation. Okay, so equation again. Now, this one, again, you know what? You need to memorize these equations, but you need to understand. For example, you need to understand that they form oxides, yeah, and how do you make formulae. But other than that, it'll help you if you just memorize these equations. Now, phosphorus plus, so it's again, phosphorus is heated in oxygen, so it's oxygen. And now, this is one of the common mistakes that students make. This is not the correct answer, okay? So they write down this P2O5. Now, there's only 2 reasons why you could be writing this down. The misconception in your head is because this is called phosphorus pentoxide. So you're thinking, oh, P2O5 for pent, yeah, pentoxide. But that's not right. Do you know why that's not right? If I ask you to write down the formula of ethane, what would it be? Yeah, I hope you're going to write down this. C4H6. You're not going to write C2H3, are you? Because you think, oh, that's the empirical formula. This is the empirical formula of that. So I'm going to write down the empirical formula, even though I asked you to write down the formula of ethane. Okay, so the formula of ethane is that. The empirical formula is this. So if I ask you to write the empirical formula of ethane, then you'd write this down. Okay, it's the same thing with phosphorus pentoxide. This is the empirical formula of phosphorus pentoxide. The actual formula of phosphorus pentoxide is actually P4O10. Yeah, that is the formula of phosphorus pentoxide. Remember that, yeah? I know we often say phosphorus pentoxide, and that's the name, yeah? But you need to remember that the that the formula of phosphorus pentoxide is P4O10, okay? Now, obviously, I need to balance it. So let's balance it. Phosphorus, so there's P4O10. So, okay, so I need 4 P's and 10 oxygens, isn't it? Yeah, so 5 here. Okay, so that could be the equation. Now, the other possibility that you can do for this is that you need to remember the phosphorus can actually exist. The element phosphorus can actually exist as a molecule of P4, so 4 phosphorus atoms bonded together. So you could write down P4 plus oxygen gives you P4O10 still, remember? Yeah, still P4O10, okay, because that's the molecule of phosphorus pentoxide. And then, of course, you need to balance it, okay, and you just write down 5 there. Yeah, so you could have written that down, or you could have written that down, but this is the more common one, okay, that you should write. Okay, observation. What did I say to you just there? I said to you, all oxides of a period 3 are white solids with the exception of sulfur dioxide, which of course is a gas, a colorless gas. Okay, so what do you think you'll see once you burn phosphorus? A white solid. By the way, this question, only 23.6% according to the examiners got both marks on it. Oh my god, why? Don't be one of them. Right, and this one wasn't done a lot better. Only 39.4% of the students got both marks for this. Yeah, and that just shows you they obviously didn't sit down and revise. Yeah, so anyway, white solid, you could have said white flame or whatever, because phosphorus, when you burn it, burns in white flame, you know, white color flame, so that's fine. You could have put that down as well. Okay, right, move on to the next part. Okay, so here it says the melting point of the highest oxides. All that means is highest oxides. All it means is the oxidation states are the highest oxidation states, yeah, in these oxides. The melting point of the highest oxides of the elements sodium to sulfur are shown in the table. Sodium, magnesium, and I'm just looking at the melting points, and I'm just looking at the trends. So okay, they're going up, so that's the highest, and then it comes down again, they reduce. Explain the increase in melting point from sodium oxide to magnesium oxide. The examiner said, for this question, students did not read the question. So they started writing about the trend, yeah, of the entire period 3 oxides. So that was the first mistake they were making. This question isn't asking you about the entire period 3 oxides. Yeah, they're only asking you from sodium to magnesium. So it is these two. Okay. And the other thing that the students made mistakes with is they started talking about elements. Yeah, the melting point of elements. Yeah, you do need to know that. You did that in year 1. Okay. However, this one is talking about oxides. All right. And the oxides melting points is what you need to talk about here. Okay. And here, think about it. Sodium oxide and magnesium oxide. Now, you should know sodium oxide and magnesium oxide. You should know that they're both ionic. Right. So there's both ionic bonding going on. So obviously, the bonding is ionic. Okay. Therefore, what is the difference? Think about it. This is in group 2. This is in group 1. So obviously the charge on this sodium is +1. The charge on magnesium is +2. So the charge density is greater on the magnesium compared to the sodium. And therefore the attraction between the oppositely charged ions here is a lot greater compared to the attraction between the oppositely charged ions of the sodium oxide. Yeah, so it's to do with the charge density being greater. So charge density in magnesium, therefore greater attraction between oppositely charged ions in magnesium oxide. Notice, did I mention metallic bonding? No, because I'm not talking about the metal magnesium, I'm talking about the magnesium oxide. So please, again, students often end up mentioning metallic bonding. Yeah, we're not talking about metals here, we're not talking about elements here. That was in year 1. Yeah, this is oxides. Of course, there could be a question on elements as well, but this is about oxides. Okay, and you lose marks if you start mentioning metallic bonding or covalent bonding, God forbid. Okay, so anyway, so charge density is greater in magnesium, therefore magnesium ion, and therefore increased attraction between oppositely charged ions in magnesium oxide compared to sodium oxide. Okay, 2 marks. Easy peasy, eh? You do need to know. Okay, it's asking you about explain why the melting point of oxide is. Okay, just so you're aware, you'd expect the aluminium. I mean, aluminium 3+. Yeah, aluminium is a 3+. This is 2+. So why isn't this melting point higher than magnesium? If we're talking about charge density, right? +1, +2. Aluminium is +3. So why isn't that melting point higher? The reason for that is this. If you look at the periodic table, you'll notice that the aluminium, which is there, and oxide, which is there, there's not much difference between there and there in terms of distance. So the difference in electronegativity between magnesium and oxygen is very large compared to aluminium and oxygen. And that means the oxygen in this ionic bonding, the oxygen cannot attract the electrons as strongly from the aluminium as it can from magnesium. And that's why this sort of a unexpectedly lower melting point exists for aluminium oxide. All right, obviously you don't need to know for this question, but they could have asked you that question. Okay, in the exam. All right, let's move on. Explain why the melting point of the oxide of silicon is much higher. So silicon is that one, much higher than that of the highest oxide of phosphorus. Now for this question, again, the periodic table, brilliant piece of concept. Okay, where is silicon? Where do you find silicon? Silicon you find in group 4. And look at what else is in group 4. Group 4, carbon. Well, what kind of structure does carbon give you? A macromolecule, right? Or a giant covalent structure. Okay, well guess what? Silicon also produces a giant covalent structure. So what you're saying is, or what you realize, is that the silicon oxide is probably, even if you didn't know, is probably producing a giant covalent structure or a macromolecule. Yeah. So explain why the melting point of the oxide of silicon is much higher than that of the highest oxide of phosphorus. Because silicon oxide is a macromolecule. And how many marks is this worth? This is worth 3 marks. So silicon dioxide is a macromolecule. Okay, because silicon is in group 4. And remember, sand. When you go to the beach, etc., and you walk into the sand, guess what that sand is? Silicon dioxide. Okay, have you ever tried burning the sand or melting the sand? Yeah, very high temperature. And the reason why, it's a macromolecule, very similar to diamond. Okay, so that's why it's got a higher melting point. Now, what about the oxide of phosphorus then? Phosphorus oxide. Well, phosphorus oxide, P4O10, is actually a simple molecular structure. And that's why, so obviously it's worth 3 marks, this question. So that means this, just writing what I've done so far, is not sufficient. Okay, so I've described what kind of bonding there is within these 2 oxides. However, what's the reason for one having a lot higher melting point than the other? So what you do is you say, oh, well, okay, so silicon dioxide is a macromolecule, and therefore there are many covalent bonds that need to be overcome in silicon dioxide. So many strong covalent bonds. Many strong covalent bonds in silicon dioxide. But in P4O10, there are just intermolecular forces. But intermolecular forces between, it's between molecules. Remember, P4O10 also has covalent bonds, but we're talking about melting. And when you melt it, what breaks? Not the covalent bonds, it's the forces between molecules. Okay, so intermolecular forces between molecules of P4O10. That's worth 3 marks. Okay, 1 mark, silicon oxide, dioxide is macromolecule, phosphorus oxide is simple molecular, and the other mark, 3rd mark, is for actually explaining so what. Yeah, why does the one have higher melting point? So many strong covalent bonds in silicon dioxide, but only intermolecular forces between molecules of P4O10. here, what the students did in the exam is they often wouldn't get full marks for this as well. And the reason for that is here they sort of start mentioning words. In this periodicity topic, the periodicity chapter, terminology is key. And that's one of the reasons why students don't get full marks, because they don't use the appropriate scientific terminology. Okay, so for example, here, all, as I said to you earlier, all, for example, you had to mention here is, metallic bonding, and that's it, you've lost a mark. Here, all you had to do here was, watch this, so many strong covalent bonds between silicon dioxide molecules. That molecules word that I've just added here, that would lose me a mark, because silicon dioxide doesn't have a molecule. It's a giant covalent structure, or it's a macromolecule. Okay, so that's worth 3 marks. Right, let's move on. A sample of the highest oxide of phosphorus was prepared in a laboratory. Describe a method for determining the melting point of the sample. State how the result obtained could be used to evaluate its purity. So describe a method, okay, and state also how the result obtained could be used to evaluate purity. So that's actually, okay, worth 3 marks, okay? So it's actually, I need 3 points. Now the first thing you've got to remember, when you're working out the melting point, when you're trying to determine the melting point of a solid, you don't dissolve it in water. You don't dissolve it in anything. You're trying to work out melting point, so why would you dissolve it? That's what some of the students put in the exams. So please, okay, when you're trying to work out a melting point of something, you just melt it, right? How do you melt it? I'm about to explain, but you do not put water in it, or you do not put it into water, etc. Be aware. Okay, let's do this. So I don't know if you've come across this, but this is called a Thiel tube. Okay, and in this Thiel tube, which has a side arm, so this side arm is all open, connected to this tube, so in this tube you put oil, a high boiling point oil. Okay, so all of that's got oil. Okay, and then what you do is you add, you just put a thermometer, so it's usually sort of some kind of a bung, a rubber bung. Okay, but the point is this thermometer's bulb is adjacent to the upper side of the sidearm. And then what you also do, your powder that you're trying to find out the melting point for, you take a capillary, a small capillary, and this capillary is actually sealed from one end, the top end. It's a very thin, fine capillary. But I'm deliberately drawing it slightly big. But it's a fine capillary, upside down, so sealed from the top, open from the bottom. And all you do is you literally just tap it into the powder. And you'll notice some of the powder's gone in. And then you turn it the right way up, so the open end is at the top. So the open end is at the top, and the the sealed end is at the bottom. And then you tap it, and the powder falls down into the capillary at the bottom. So you'll see that white powder, or whatever color it is, in this case white powder, you'll see that at the bottom of the capillary. And then that capillary, remember this is a small capillary, this pencil is quite big, but this is a small capillary. So what you then do is when you've got a bit of powder at the bottom of that capillary, you attach that to, before you put the thermometer in the Thiel tube, you attach that to the thermometer. And you can use a rubber bung or whatever to attach them. And then what you do, you heat. But you heat the side, of the sidearm. Okay, you don't heat the main tube. The reason is that when this oil gets heated up, it will flow towards that, and of course a cold oil will take its place, and eventually you'll have some kind of convection current going on. Okay, and of course when this oil reaches the temperature, the melting point of this powder will melt. Okay, now obviously this is the older versions. Nowadays you can get these melting point apparatus, where you put it into this powder into the capillary and then just put it into the melting point apparatus. Okay, so you can use either, but anyway, you can mention either. All right, so anyway, the point is, and let's just mention, obviously you don't need to draw this diagram, that takes a lot of time. They're not asking you to draw a diagram. You can if you want to, but let's describe it. Describe a method for determining, you can use a Thiel tube. Use a Thiel tube, place a sample in it. You don't need to describe all of what I've just done, I told you this just in case you're not aware of it, But they're not asking for, it's only worth 3 marks. They're not asking for sort of full, 6-mark method question, right? So anyway, one, use a Thiel tube, place a sample in it. Okay, step 2, then you heat it, but you heat it gently. Yeah, it's not a roaring flame, right? So heat gently, because remember, this might melt very quickly. You don't want it to melt very quickly. You want to know what temperature it melts at. Okay, so heat it gently, and then of course you can say note down the range of temperature at which the powder melts. Okay, now, okay, well, that is the first part. Describe a method for determining the melting point of the sample. Okay, I'm not done the second part. State how the result obtained could be used to evaluate its purity. Well, you need to know this, and if you've done this method, this practical in your college or school, then you'll know this. And if you're not, I think you need to find out. Okay, well, you need to know that a pure sample, the range which it melts. So what you'll see is when you actually melt it, you'll notice the powder beginning to melt. And then you'll notice it when it's completely melted. That's the range you need. So let's say, I don't know, that it starts to melt at 200 degrees. And then it finishes all that powder melting at 250 degrees. So the two things that you're looking at is the range. That's quite a wide range, 50 degrees. Yeah, it takes a long time. And therefore, if it's a big range, it means it's impure. Okay? If it's a very small range, that means it's pure. And the other thing that you should be looking at, not just the range, but the other thing is the actual temperature. Yeah, so okay, it's all very well at 200, 205. Yeah, the range is small, but what if the actual temperature, the theoretical, the melting point of this powder was 400 degrees? Yeah, okay, well, the range is small, but it's way out. Yeah, so you should be looking at the actual temperature. So small range is pure, and then of course what you can say is you can simply say, what does it say? State how the result obtained could be used to evaluate. Yeah, so you can look at the range and also compare with theoretical melting point. And if it's close to the theoretical melting point, then it's pure. If it's not, it's not. Okay. So for 3 marks, So, you should mention there's some kind of apparatus. So it could be use of Thiel tube, or it could be melting point apparatus, because nowadays you do have these electrical heated melting point apparatus that you can use. Yeah. So as long as you mentioned some kind of an apparatus. Yeah. And then of course the other thing that was key was heating it, and heating it gently. Because remember, you don't want sort of roaring fire at it, yeah, because before you know it, it melts, and then you think, oh my God, the temperature's gone to 10 degrees higher. I don't know what it was. Anyway, so gently, that was a key thing. So that's the 1 mark. That's a second mark, and the third mark is either one of these. Actually, you could talk about the range, or you can talk about comparing the melting point with the theoretical melting point, with a book value or theoretical value. Okay, so that's a third mark. Okay, as I said before, this topic, students often lose marks, and that's because 2 reasons. 1, they've not sat down and actually memorized equations, okay, and understood the melting points, for example. Yeah, why are the melting points higher or lower? So that's the first thing. And second thing is terminology. Yeah, they use the wrong terminology. Yeah, so when they want to talk about sort of metallic bonds, they end up talking about ionic bonds. Yeah, or ions. Yeah, so metallic bonds between ions, or ionic bonds between molecules. Yeah, so you can't really get ionic bonds between molecules. It's either ionic bonds or between ions, or intermolecular forces between molecules. Yeah, so you've got to use the correct terminology, or using sort of the word molecules when you're talking about ionic compounds. Yeah, in ionic compounds, remember, why do we not say ionic molecules? That's because there are no molecules in ionic substances. That's why we call them ionic compounds. Okay, so please be careful of using the correct terminology, but also sit down and memorize. Yeah, no 2 ways about it. Some of these things you just got to sit down and do the work, do the hard grind, as they say. Okay, right, I hope that was useful. Again, if you've got any suggestions, please put them down in the comments below. I obviously have other inorganic videos, for year 1. Yeah, have a look. I'll put it up here somewhere. Please like, share, subscribe, okay, and I'll see you next Wednesday.